Hello, hello, Maria. Hello, Chris. Hello, Yavi. Hello, Cheska. Hello, Shawnee. Hello, Katie. Hello, Emily. Hello, good afternoon. She will not give an adjective. They will not give an adjective, ladies and gentlemen. All right, but hello, yes, hello, Shawnee. Afternoon, Maria. Hello, Michelle. I'll take an extra O over an adjective any day. Good afternoon, Jada. Good afternoon, Katie. Good afternoon. What was it? What is that? Oh, I see that. I saw that digital multimeter. Oh, are you up to that in Okay, noted. Totally noted. We are not going to discuss that today, but noted. Okay.
No, I'm not uploading in lab. I just have it on.
Oh, that's even cooler. Or that's a flex, I think. All right, but that's cool. I'm down with digital multimedia, and you will be doing those. All right, anyway, I will not get off or actually, why am I nervous? Yeah, I'm not anyway. Good afternoon, Freddie. Wait, I see Freddie, but I don't see Freddie. Oh, yeah, okay. Good afternoon, Freddie. Good afternoon, Stephanie. Good afternoon, Yavi. Good afternoon, Marilyn. Good afternoon, Emily. Good afternoon, Allison. Good afternoon, Brooke. Li Oh, interesting, Maria. Okay, Maria, fair enough. Challenge accepted. Challenge accepted. Good afternoon, Victoria. I don't know, is it listen or is it read the chat? Anyway, yes, challenge accepted. Hello, I'm going to don't electrocute yourself. That would be shocking. Okay. Good afternoon, Paulina. And you know what? Well, okay, we're not going to make all the obvious, like resistance is futile. Okay, yeah. Okay, wait, who else am I not? So hello. I see what does she do? Okay. Okay. Wait. Quick announcements. I'm glad you're all here. I'm actually impressed you're all here, or I'm impressed that those of you who are here, because I do know it's like slightly awkward to have a class like in the middle of while your exam is still due, and it is, right? Like we said it's due this Wednesday because you have your yes, it is awkward. Okay, fair enough. But it's a consent, we made that concession hopefully to help you all with your conflict with chemistry. I don't know if it's really helping that much, but that was the idea. But so the exam is due Wednesday at 12:15. Now that the exam has started, really it's not appropriate. It still is appropriate for you all to talk about it amongst yourselves. That's fine. That's the kind of exam it is. But me actually giving help is not appropriate, largely just because some people have more access to me than others. So that just would be whatever, like unfair, I think. But so the awkward part is we are going to go. So I'm glad you're here though, because we're going to continue with the material today. Um, I'll, yeah, I can't really pretend that this will directly help you with your exam. If I think of things to say that can, I'll say them if I could say them to the whole group. But your reason you're here today to pay attention, awkwardly as it is to get help from me or to get new learning with regard to the Doppler effect, which in my understanding, I think happened in lab recently or is now on the docket in lab. And there's been this homework in the background forever. Like in theory, it was due 1,000,000 years ago, but not. About the Doppler effect that now is going to be the next thing that's due after this exam. In other words, you might have just noticed in Google Classroom, it's due. It's now going to be due a week from today. So you hand in the exam this Wednesday, and then you're going to deal with this Doppler effect homework for Monday. So even though I know it's a little bit tricky, everything I'm going to tell you now, even if you're only paying attention with half of a mind, but yet writing it down, whatever you're going to write down today or get the notes for today, I would encourage you to consult when you try to do the homework about the Doppler effect for Monday. Also know, of course, sidebar, usually this material does appear in this form on the final exam. We'll talk about that. So it's like not dropping into a vacuum. Also, I think it's super interesting material, but whatever. So we're in a minute. The board meeting. Okay, thank you, Shawnee. Okay, so you did the board meeting on the Doppler effect. Great. So as always, it's often the case that you first see something in lab and it's like confusing and new and sort of out of left field. And then you're like messing with stuff and doing something, sort of trying to make the most of it, and then we get to lecture. and try to clarify. Not everybody likes that. I know not everybody likes that sequence, but it's not an accident. It's not about liking it. It's about that. I mean, in the long run, I hope you appreciate it. But the reason we do it that way is because, like, that's how physics works. Like, you first discover things in the physical world that are confusing and that you play around with and try to make some sense of. And then you come out of the lab or out of the arena of space time and you go back to your desk and you try to make theoretical or mathematical or analytical sense out of the world. We're trying to reinforce that, like, even when physics seems really theoretical, which maybe it does, when it seems really theoretical or really abstractly mathematical, it's still always an attempt for us to explain the complex, to in fact simplify the complexity of the physical world of space and time. So, like, that is how it goes. We wouldn't care if we didn't live in a world. I mean, probably care, but we would have a whole different set of things to say. So we're going to deal with Doppler effect today. And hopefully it'll start making some more sense to you what it is that you've been talking about in the lab. Since Shawnee just said it was a board meeting, I'm going to gather that that means maybe that you don't have a lab report to worry about the Doppler effect. So that's great. So the reason you're going to worry about it is because now it feeds into our material in lecture, into the homework, and ultimately into the final exam. Also, it's like, I think one of the most like it's a super interesting and very real topic, I think. But last thing before we go to that, before we go, wait, sorry. Oh, that's not what I meant. Hello, hold on. If I'm not careful, we're all of a sudden going to end up in the middle of a Pokemon battle. Hold on. I mean to do this. Yeah. Okay. We're going to do the Doppler effect today, or try to set it up so that you can do the homework. But last announcement, it's that time of the, just so you know, I mean, happy holidays to everybody of various kinds. But I know it's also the time of year, just to be blunt, a lot of people are applying for a lot of programs, such as, for example, a number of you are, I, I mean, I don't think I'm giving anything away to say, a number of you are applying for the BS/MS program in forensic science, which I'm very happy about. I'm happy the program now exists. I'm happy that a number of you are applying for it, and I hope every single one of you gets in it and sticks around John Jay a little bit longer. Like, honestly, I think it's a great program and I have a vested interest in keeping you around. So just to be clear, for those of you who are applying and who have asked me for letters, I know your applications are all due today. My letters have been coming in steadily through the day. They'll continue to come in through tonight, just so that you also know it's always okay if the recommendation comes in like a day after the application. That never hurts the application. I promise. I know this from experience. But if you haven't gotten a confirmation yet that your recommendation letter's in, just know that I know, and they're all in progress. There's definitely not forgotten, and the order is somewhat arbitrary. But if you don't see confirmation land in your box, like in the next couple of days or when you're done with your exam, definitely ping me and say, just want to make sure it landed, and it will, and it will. And obviously I know the people involved in all of that. I mean, I know the faculty members who are the admission committee and all that. So believe me, I'm very happy to support those of you who I am, and it's all happening. All right, just want to say that. So don't worry if you haven't seen confirmation yet. Okay. Yeah, no, I do. I go kind of crazy with these letters, and whatever. Of course, they all know all the people reading them know I'm crazy and they don't take them serious. No, I'm just kidding. Okay. So that's just again to say, I know there's some of you sitting in the room yet that have not received a confirmation yet. Don't worry. Like, that does not, there's no problem. It doesn't mean there's a problem. Or it's forgotten or anything. Okay. So we're going to talk Doppler effect now. Okay. So we're going to talk Doppler. I mean, you could stop me if you have, and even if, by the way, even if in the back, I'm trying to keep this curriculum going. In the background, if there's something that you're freaking out, no, I don't want to really invite this, but if there's something like logistical, like, I think there was like a mistake or a confusion in the instructions about the exam that I tried to clarify, but somebody caught. Just to be clear, you're handing in a total of 2 problems for the exam, like one from the first pair. There's 4 problems in the exam. You're choosing one from the first 2. and you're choosing one from the second two and turning that in as your exam. If that's not clear, definitely let me know in direct chat or whatever. And you don't get extra credit for doing more, and you don't get extra credit for doing partial problems. Like, don't do partial problems, do all of one and all of another, blah, 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 blah. So if there's any issues like that or logistical or like, wait, what time, put in the direct chat, but I'm sort of assuming that it's sort of clear if I don't hear otherwise. So Doppler effect, the equations that you got to know to do the Doppler effect are right here. To do any Doppler effect problem, in fact, here's a summary. Okay. Doppler effect. I'm gonna lay it all out, but a Doppler effect is a phenomenon that exists in nature that has specifically to do with waves. I will write it out in a minute, but the Doppler effect, a phenomenon that is associated only with wave motion, is a phenomenon that is frequently or frequently associated with sound waves. Like, we know it we experience it very commonly when it comes to sound, but it's something that applies to any kind of wave. I'm going to define it in a minute, but just to give you the overview, the general thing of a Doppler effect, the general playing out of the Doppler effect arises in one of four possible cases. There's four different typical ways the Doppler effect can arise. And our ultimate job in this class is to be able to compare and contrast the results from those four cases. Like, that's the ultimate goal, is to be able to calculate final answers for any of the four cases and be able to understand why you get one answer for one case and a different answer for a different case. Okay, this is just a broad overview. The equations that are needed to solve any Doppler effect problem are the ones that are on the board right now. Obviously, I'm going to back up in a minute and like break down these equations in a way or show you how to use them in the Doppler effect. But I want you to note two things before I go any further. One, the top equation right here on the board, V equals lambda F, that is one of, should I just write this? All right, yeah, I'll start expanding right now. Even before I even explain like exactly how to do the Doppler effect or exactly what it is, I want you to note, first of all, V equals lambda F is equivalent to saying any of the following. Oops. Well, yeah, those would be the two main. Okay. First of all, before I get into all the details of the Doppler effect, I want to make it clear that the one like sort of new equation, the equation that the whole Doppler effect phenomenon is based on, is this equation that is generally written in textbooks and websites as V equals lambda F, V equals wavelength times frequency. That is an equation that applies to a wave. In English, it's really just saying something we've always known in physics. It's really saying that average speed is defined to be distance divided by time, right? In other words, this equation, when we say that the speed of a wave is its wavelength times its frequency, first of all, like, where did I even get that? That's just equivalent to what we derived before we got into all the exam, like 2 weeks ago, when we did the wave equation, the second order partial differential equation, and we had this omega over k term in the equation. We derived 2 weeks ago that V equals omega over, that we derived that omega over k, angular frequency divided by angular wave number, is just another way of saying wavelength over period. And we know for, I mean, see, there's all these different interchangeable ways of saying the same thing. They all just depend on context. We know that the frequency of an oscillator or wave or whatever is necessarily the reciprocal of the period. We've known this for what? Like, again, that's just a way, standard frequency is reciprocal of period. It's just a way of saying, like, if it takes you 4 hours to run around the track, then you run 1/4. Sorry, if it takes you 4 hours to run a lap around the track, then you run 1/4 of a lap every hour, right? Like seriously, like, think about that in your head for a second, or write it down. Like, the frequency with which you complete cycles is the inverse of the amount of time it takes you to complete cycles, right? We've been saying that from the start, for a while. So when we derived last week that angular frequency over angular wave number is just the same thing as, like, how far it is from one crest to the next divided by how much time it takes to get from one crest to the next, what we're ultimately saying is, no matter how you write it, omega over k, lambda over t, or lambda times f, what you're saying in the end is how many meters pass by from one crest to the next of a wave per every number of seconds that it takes to wait from one crest to the next. So any one of these is a way of expressing the speed of a wave, but and the way it's kind of like with harmonic oscillation, like, the most mathematically direct way of talking about speed is omega over k. That's what comes out of all the math. But the most common physical, like laboratory, common website, textbook way, and PChem way of talking about the speed of a wave is to talk about its wavelength times its frequency. If the wavelength is 3 and the frequency is if the wavelength is 9 and the frequency is 3, that means there's 9 meters from crest to crest, and it means that if the frequency is 3, that means there's 3 crests every second. So if there's 9 meters between every 2 crests and there's 3 crests every second, then the whole wave is traveling 27 meters per second. Like, that's what we're saying with this, okay? And that's what I'm going to say from now on. So that's a description of waves. Like, that's a wave description from now on, that the speed of a wave is the wavelength times the frequency. But before I go any further, the key takeaway that we got, and this is like a really big deal. Okay, let me take a breath and try to get. In fact, let me even change the view of the screen. This is such a big deal. Hold on a second. I mean, it really is. Hold on. Okay. just like with simple harmonic oscillation, which this is all built from, right? From simple harmonic oscillation, the big takeaway, really, the big conceptual theme of simple harmonic oscillation is that the frequency of an oscillator is independent, the frequency of a harmonic oscillator is necessarily independent of its amplitude, right? Like that's a mouthful, but this is like our big point is that once you and furthermore, or more specifically, like the angular frequency, therefore the frequency, therefore the period, the cycling rate of any harmonic oscillator is entirely fixed, determined by the oscillator's parameters, right? Like if you have a mass on a spring, if you know how massive the mass is, if you know how big the mass is, and you know how strong the spring is, if you know K and M, then you automatically know omega, right? Omega's the angular frequency, the cycling rate, like, and that's measured in radians per second, but then you can automatically convert that to cycles per second, and you can automatically convert that to seconds per cycle. So if you know the ingredients of your simple harmonic oscillator, you automatically know how fast how quickly, rapidly it's going to cycle back and forth, right? And you know that even if you set up the oscillator like this, or you set it up like this, like it doesn't matter what amplitude you give it. It doesn't matter how far apart you initially stretch that spring. It will, if it's going to take 2 seconds to go back and forth, then it's going to take 2 seconds to go back and forth, no matter where you started from. Now that's like a bit, in other words, harmonic oscillators are clocks. They measure time regularly, irrespective of how they're arranged in space, right? Now that's the big thing of oscillators, harmonic oscillators. But then all of our math and all of our analysis is saying, if you want to make a wave, what you do is you arrange a bunch of oscillators in a very specific way. Now, all these oscillators are little clocks that are just vibrating at a certain rate, no matter where they are or how much they're stretched, like no matter how they're arranged. And a wave pulse is like a sequencing of all these little clocks, right? Like when a pulse goes through all of them, it's because they're each going up and down at a certain tick-tock rate, and they're all like arranged next to each other in a certain phase pattern, right? So what we're arguing in the end is, if a wave pulse is just like the result of a bunch of little tick-tock, tick-tock, tick-tocks, then the wave pulse, the speed at which, and I mean, literally, if the wave pulse is omega over K, and omega is always fully determined by parameters, and in effect, so is K. I mean, it's like a harder argument to make, but it comes to the same thing. So if the speed at which a pulse propagates through a medium is fully determined by the oscillation rate of all of the oscillators comprising that medium, then, and if all those oscillation rates are just based on the materials making up that medium, then what we're saying is, once you send a pulse through, once you know the medium, once you know I had this heavy masses on these strong springs and I put them all together and I made a wave, once you know what your ingredients are, once you know what the material oscillators are making the medium through which you're going to drive a pulse, then you automatically know the speed at which the pulse goes through. This is 2 important points now. Number one, it means that let me say this, I'll say this as clearly as I can. So number one, as long as the medium is constant, then the speed is constant. That's number one. Right? I.e., there's no acceleration. Like, and think about that for a second. Like half of what made Physics 203, like a class that you have to take, half of the hard work we do in classical mechanics, half of it is dealing with the issue of acceleration, like more than half, really. Well, I don't want to get all into a whole rabbit hole, but like so much of it, of physics, is about the relationship between acceleration and velocity. And here now we're saying once you make a wave, you don't even have to worry about acceleration. As long as you're creating a medium for a wave and your medium is regular, is uniform, then the wave is just going to go at constant velocity. Like that is like remarkable simplification of motion. I mean, it makes both the predictions and the analysis and everything like much more smooth and simple, right? But the other thing is that, and I am saying that, like, this is why we care so much about waves. Like, they're very reliable, like in a way that baseballs and electrons and planets are not. But then the second thing is that it means that V, this V is measured, the value of V, the magnitude of V, it means that whenever we talk about this constant speed, we mean relative to the medium. This brings it, like, remember now, this is the other big part of physics 203, that the huge theme in physics 203 is that velocity is a relationship between two objects. It is not a property of one object, right? It doesn't mean anything to say, how fast is the Earth moving? It means something to say, how fast is the Earth moving relative to the sun or relative to my feet, which are two different answers, and they're both legitimate in their own frame of reference, right? The Earth is going 0 relative to my feet, thank goodness, so I can stand stably, not fall over and puke all the time. But the Earth is at the same time going 65,000 miles an hour relative to the sun. And that's not a contradiction, because velocity is a comparison in and of it, right? It is not a thing that an object has. It's a relation that one object bears to another object. We've been saying that, and that's right? So in fact, so okay, I'm going to pause for a second. I still haven't even said what a Doppler effect is, I know, but I'm giving the two. What a Doppler effect is two big pieces of our understanding of motion coming together into one. What a Doppler effect is, whatever it is something, and I know you know, I mean, I know you did the lab board meeting, and also, like, what is a Doppler effect? It's this, like, that's the Doppler effect, right? I mean, obviously, I'm going to explain it better, but like, we all have some intuitive familiarity with the Doppler effect. The Doppler effect is the idea that a car goes past you or a motorcycle or an ambulance goes past you in New York City, and you don't hear unless you're in the car. If you're in a car and you're like, you fall, no, I don't want to. If you're in a car and you hold down the horn, and you're in the car, you hold down the horn, it's one constant note, you'll hear but if you're outside, if you're not in the car and the car is coming toward you, and then passing you, that's not what I mean to say. If the car is coming toward you, and then it passes you, and then it's going away from you, then you all know, being New Yorker, like, you know, what you hear is something more like, okay, that was, but right? I mean, you hear a high note and then a low note. That's the Doppler effect. Now, I'm still going to break it down, obviously. But, oh, wait, sorry. Oh, sorry. Yeah, and I'm not even defining it yet. Right. I mean, and it's a choice. Fair enough. I mean, and maybe this is a weird choice on my part. What I'm telling you right now is I'm telling you the two ingredients that come, and partly I'm doing this because I feel like you already sort of have some kind of definition or something from lab, but right. Before I even define it, what I'm saying now, there's two things that come together to make a Doppler effect. There's our new understanding that wave speed is always constant relative to its medium. And then there's our memory of, oh yeah, relative to, that all velocities are always measured one relative to another, and that's an important feature of how to analyze velocity in general. So what I'm about to say that the Doppler effect is what happens when this equation meets, or when wave motion, let me back up. What the Doppler effect is when the relativity of velocity is applied to wave motion. That's what it is. It's when the relational character of velocity is applied or plays itself out in the motion of a wave as opposed to a particle. And the relative, that still isn't a definition, by the way. That's like an introductory observation. What I just want to remind you before I go any further, when I say that velocity is a relation between two objects rather than a property of one, when I remind you of Galileo's principle of relativity from last semester, which I always say is like a really, really big deal, and like no one ever believes me until they do. Like, it's a really big deal. Let me remind you that let me remind you of what we used to call GPR form number 4. What we call in other words, the first time that we started expressing Galileo's principle of relativity in a symbolic or mathematical or quantitative way, we thought of it in 3 cases: the 1 object case, the 2 object case, and the 3 object case. We said, if you have 1 object, so we said, like, imagine you have 3 different objects with 3 different velocities, objects A, B, and C. Let A, B, and C be 3 distinct objects, or 3 random objects with 3 distinct velocities. Right? Then we said, in the 1 object case, when you're only looking at object A, we said necessarily what relativity means, what the principle of relativity, and remember, the principle of relativity in English is the laws of physics are the same in all inertial reference frames. The laws of physics, whatever they are, hold the same at every different constant velocity. The laws of physics don't change from an elevator to an airplane to a planet. It doesn't matter how fast you're going, as long as you're going at a constant speed in a constant direction. The laws of physics are still the same. Like, that's the principle, and that's why, right? That's the principle. And how it plays out mathematically, it plays out in many all areas of physics. But how it plays out mathematically is, if you have 1 object A, then the velocity of an object A relative to itself is always 0. Right? That's the 1 object case. Nothing is moving to itself. The Earth is not moving from the reference frame of the Earth, or the Earth is not moving compared to the Earth. And again, I remember we had a fun time. Everybody was sort of buying this and buying Form 2, as long as we think about video games and stuff like that. Like, especially if you're in a first-person video game, if you play video games, if you're in a first person, even like a first person shooter, which is not my cup of tea, but like, if you're in a like, you're not, like, they just show the goggles or the gun or the whatever, or in Minecraft, if you're in first person, right, and they just show you like mining thing going like this, like, that never walks away from you. If you're in first person view, it's always there. You're always with you, like, duh. Right? And the whole world is coming by you. That's like the reason that works in video games. The reason everybody is because that is the way reality works. You are never moving relative to yourself. So that's the 1 object case. The 2 object case is if you are moving relative to something else. And by the way, I'm reviewing this now partly to review, but because we need this for the Doppler effect. It's not a tangent. I still would like to address Katie's right that I should get to a definition like before the end of the day. But as long as I'm on this tear, the 2 object implication of Galileo's principle of relativity is that if you are moving relative to some other object, if you are object A and you're moving at 10 miles an hour to the east past object B, then necessarily what B will observe and measure is that B is going in the I just said it backwards, but if you're going past B, then B is going past you in the opposite direction, necessarily. Right? And again, this is captured in video games, and it's also visible on the highway when you pass another car or whatever. Like, if that car sees you go past it forward, then what do you see out your window? You see that car go backwards, right? And the thing that physics is saying, that's not an optical illusion. That is the nature of velocity. And neither one of you is any more correct than the other, right? You could say, well, but really what's happening is I'm going forward and like they're just like I mean, it looks like they're going backwards, but they're not really. But no, like what's really is that you're both on an Earth that's going 65,000 miles, but like you're not really doing anything that's any more interesting than what that car is doing. For all you know, you're traveling west you're traveling east while the Earth is traveling west. So actually, really, past the sun, you're going 64,000 miles an hour in the other way, but you're not. But then the sun is going past the galactic center, blah, 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 blah. So like there's no really about it, is what the real issue is that velocity is a perspective. It's a relation between two objects, and that relation is symmetric. If I go past you to the east, you go past me to the west. Now that's the two object case. Now, again, most of you, I even remember where I was sitting when a lot of you were still like with this at this point. You might not have known it was science, but like, you know what I'm saying. And the beautiful thing is it is science. But then the kicker that we totally need, and then I'm going to say this, and then I'll take a breath, and I will totally address Katie's legitimate point. The kicker, I'm going to go to the other page, is the three object case. The three object case, which everybody knows in simple versions of it, but everybody gets a little bit like wonked around in the complicated versions of it. The three object case, just to remind you, and we'll now see this play out with the Doppler effect. The three object case is that velocities add like vectors. And this is actually quite an insight. But the simple, I'll say it in English now. And again, this is where many of you, and we had an exam about this. Obviously, I know some of you weren't in my class, but like somewhere along the line, like people have gotten physics problems about this idea, and this idea is no joke. And people definitely last semester were like, whoa, you lost me on this one. Now, I'm not going to redo the whole the whole thing, but the summary is that once you have three objects, now you have more than one velocity involved. Like you have a velocity of A relative to B, but you have a velocity. I mean, if velocity is a relation between two objects, then once you have three objects, you got a bunch of velocities going on. And the velocities combine in a certain way. They do. Like they relate. The relations relate to one another, but in a very specific way. The way velocities work is that they add like vectors, even when we're in three dimensions and whatnot. The velocity of me relative to you plus the velocity of you relative to the sun equals the velocity of me relative to the sun. That's a little abstract. But more specifically, the example that we all know that we talk about a lot is like the velocity of me relative to a subway plus so pretend I'm A and the subway is B, and pretend that the streets of New York, like the grid, like the streets, are object C, or the ground, whatever you want to say. The velocity of me relative to the subway plus the velocity of the subway relative to the ground equals the velocity of me relative to the ground. And that's why I take subways, because I can stand or sit on a subway and be at zero relative to the subway, right? Like I can sit there and I'm sitting next to you and you're seeing me and I'm not moving anywhere relative to the subway. I'm chilling. I'm going zero relative to the subway, but the subway is going 100 miles, 75 miles an hour relative to the streets. Therefore, I'm going 75 miles an hour relative to the streets with no effort. That's how velocities work. Now, what's crazy is that's not just because I'm inside the car. Even if I were outside the car, that would be true. And even if I weren't going zero, like if you throw a ball, and I don't want to get into, we can get into but if you drop a bomb out of an airplane or whatever, like it doesn't matter whether objects are inside or outside. It doesn't matter whether the numbers are zero or not. It doesn't matter if there's negative signs, and it doesn't matter if there's angles. Velocities literally add like this, and nothing has to touch anything else. It has nothing to do with forces or motors or engines or anything. It's the nature of motion that it works like this. Now, and I'm not saying that's easy. In fact, that's very hard to really get your mind around. But we got our minds around it to some extent last year. We're going to get our minds around it again this year or this semester. But hopefully you at least vaguely remember that it's vaguely true. Now, what I'm saying is that when Oh, wait, do I want to say one more thing? No, I don't. Okay, when, so I'm almost at a rigorous definition here. I'm almost at Katie's point. But when, okay, that's not a definition. That's just a statement. Now I'm about to give you a definition in a moment, but I'm just saying there, the reason I'm talking and reminding you about the relativistic or the relational character of velocity is because, and by the way, I'm reminding you, like the reason we did that in physics 203 is because these three, like VAC equals VAB, like this business, it's always true of velocity. Sometimes we care more often, like in more intensely than other times. But it's all like sometimes in a physics problem, it's just understood that everything we're measuring is all relative to Earth. So we don't like have to worry about this as much, or it doesn't get as confusing or surprising. But it's always the case. It's always the case that velocity is a relation between two objects. It's never a property of one. That is always the case. And then there's this case now, or now there's a situation where we have this thing called waves, where the velocity of a wave is always constant relative to its medium. Relative to its medium. So when those two statements connect together, that a wave always has a speed that is always constant relative to, like compared to, like measured by its medium. When we say that, and then we like think hard or remember what relativity ends up meaning, that it means that velocities add this way. Or in other words, if we then say, well, what does that mean? Like, what do you mean the velocity of a wave is always relative to its medium? Like, as opposed to what? Like, you mean like the medium of the wave could like move past something else and something could happen or something? Yes. What we're ultimately saying is the velocity of a wave is always relative to its medium. But no one ever said that the medium is like absolutely stationary in the universe, or like no one ever said the medium can't move past an observer or past a transmitter, or that a transmitter or a receiver can't move past a medium. And in fact, it happens all the time. So in fact, what I'm going to say right now is here's a definition. Well, here, I'll write definition right to make it clear. Okay, wait, as usual, the most important thing I just like squeezed into the bottom of the page. I may rewrite this in a second, so it's not, so you don't lose the main. Oh, can you hear me? Wait. Shawnee, you can hear? Okay, okay. I may recopy this in a second just because like the most important thing just got squeezed to the bottom, but this is correct. What it says is, so the definition of the Doppler effect from here on in is when the source of a wave and or the receiver of a wave is moving relative to the medium for the wave's medium, so that's a condition for the Doppler effect. Then the source will not measure the same wave frequency as the receiver. I'm going to say that one more time because that's like, so, again, I mean, like Katie was right to ask. I think we definitely need a definition. I'm going to say it again, then I'm going to try to explain it more. But I'm saying, and really what this definition is, it's like a condition and a result. So the condition that has to be met for there to be a Doppler effect is that something is sending a wave to something else. A source is sending a wave to a receiver. And then as long as either or both, if either the source or the receiver is not stationary relative to the medium, if either the source is moving through the medium or the medium is moving past the source or the receiver is moving past the medium or the medium is moving past the receiver, which is the same thing, but right, if there's any kind of non-stillness between either the source and the medium and or the receiver and the medium, then first of all, then just back up and realize, well, then whatever that constant speed of the wave is that's measured relative to the medium will be like some other number to at least the receiver or the source, right? Like that's really what we're saying here now is we're backing up and saying, hang on, a wave always goes at the same speed relative to its medium. But like it is possible for you to run past the medium while you're trying to catch a wave, or it's possible for the medium to run past you while you're trying to throw a wave. So if that happens, if either of those happens, then at least somebody in the whole situation doesn't agree with somebody else on the speed at which this wave is moving. That's like the condition I'm saying. Obviously, we're going to play this out in numbers, but then the result, the thing that we all recognize as the Doppler effect is a disagreement in frequency measurements. This is the key. Now, again, but the key, what is the Doppler effect really? When I say that the Doppler effect is, which I will, what I merely mean is a Doppler effect is that a source of a wave and a receiver of the wave disagree on the frequency of that wave. And when I say disagree, I don't mean like they have an argument because they're like temperamental. And I also don't mean like that one of them like experiences an illusion. I mean when the source of a wave and a receiver of a wave obtain two equally legitimate but different measurements for the frequency of one and the same wave. When a source of a wave is not in the same frame of reference as the receiver of a wave, and therefore, at the end of the day, gets a different frequency measurement on that wave. That is what we mean by the Doppler effect. I mean, and whenever X happens, Y happens. Whenever the condition is met, the frequencies do differ. Okay, so I'll say it one more time, or I'll say it a slightly different way, because there's a lot of things that seem like they're the Doppler effect, but that aren't. So put it one last, more firm way. The Doppler effect so like i.e. the Doppler effect is a disagreement. See, that makes it sound like, wait, I don't like that word actually. Is two differing measurements for wave frequency. It's all about frequency due to two different reference frames for wave measurement. And when I say, so I'm saying Doppler effect is disagreement over frequency due to disagreement over frame of reference, and again, differing measurements over frequency due to different measurements over frame of reference over velocity, and when I say two different, the two that I mean always, so vis-a-vis source versus receiver. So when the source and the receiver of a wave are in two different frames of reference, because one of them is moving at one speed relative to the medium, and the other is moving at a different speed relative to the medium, maybe one of those numbers is zero, but as long as one of them is not zero, as long as the source and the receiver of a wave are at two different speeds relative to the wave's medium, then they will measure two different frequencies for that wave. That's what the Doppler effect is. Now, obviously, we still have to do math and everything, but now to start applying. So I'm saying what all of those words is, what all those words mean is in the end, but like, how am I saying? And by quick sidebar, notice what I'm not saying. Doppler effect, well, I guess I'll get into this now. Doppler effect does not have to do with amplitude, and Doppler effect does not have to do with position. It feels like it. A lot of people think it seems like it has something to do with how loud something is based on where you're standing or how far away you are. That's not what it is. It's how high pitched something is based on how fast you're moving. Okay. In short, in English, the Doppler effect is disagreements over pitch, like note, based on how fast things are going and in what direction. It's not a disagreement over volume based on where things are standing. Okay, so let me now start breaking that. Okay, so this is the overall picture of the Doppler effect. Now, let me get into like slightly more mathy things or whatever, but first to make a couple more connections. Oh, I think there's something in the chat. Okay, 1 second. Hold on. I see something in the chat. Give me. I was totally looking. 1 second. Two. Okay, we have to note a couple of things first. Let me just see what's in the chat. So we're going to note something. We're going to note how the brain interprets various aspects of a wave, but in order to basically, I want to note how this applies to specifically sound waves so that you can relate to the thing. But wait, but first chat. Let me just see what it says in the chat. Okay, it's direct chat. Oh, wait. I've got to read this question out loud. Okay, hold on. But I'm just deciding whether I'm going to read it right now or if I'm going to pause for a second first. Okay, there's a question in the chat. There's one question, so you know who you are. I'm totally going to read this out loud and answer it in a moment. Remind me if I lose track. Let me just say one thing first before I answer that. And on purpose, because I want to say this, but I don't want to dwell on it. So first note, Ran out of room again. Okay, one quick thing to say before I get to this chat question. Like everything I've said thus far in the class today, everything I've said thus far is about waves in general. Like anything that's a wave can produce a Doppler effect. And then it has observable features that you'll note that you don't necessarily always know are a Doppler effect unless you know. But like you can notice a Doppler effect in any kind of wave, including water waves. I don't want to get into it, but you don't necessarily know that they're Doppler effects, but they are. Whatever. Any wave can experience a Doppler effect. Also, light waves in a very, very important way experience a Doppler effect. But the most common, the thing that we're talking about right now, the thing we can relate to is sound waves. So before I go any further, I just have to clarify sound waves. And I really, I should, okay, I'll even say, oh, hello, sorry. Just so you know, a sound wave, I know this is getting crowded, but sound waves, strictly speaking, are what's known as compression waves or longitudinal waves, as opposed to transverse waves. Now, okay, again, you make a note of this. Like whenever you've been doing waves in the lab, especially lab 3, like when you shake the string and you send crests and troughs. When you send crests and troughs that are going like this, but they're moving back and forth along a horizontal string. When you set up a situation and when you do problem 4 for the exam, I mean, if you choose to do it, all of those pictures in our mind are assuming that oscillation is on one axis and propagation is perpendicular to that axis. All the drawings and the mental reflections that we're doing and the lab visualizations of long strings, those are all situations where oscillation is the oscillation axis is perpendicular to, or so to speak, across the propagation axis. Those kind of waves are called transverse. Trans means across. So water waves, string waves, where the bumps up and down are then flowing side to side, that's called transverse. Now, in truth, not all waves have to be that way. If you pick a medium such as air molecules, you can set up a situation where you have a bunch of air molecules between you and me, and the air molecules over here vibrate back and forth or oscillate back and forth like this, rather than up and down. They oscillate forward and back. And then the next air molecules oscillate forward and back. And then so what you really have with air molecules, it's like if you took a long slinky and you flicked one edge of it, instead of shaking the slinky, you flicked it. So you saw pieces of the slinky get close together and then far apart and then close together and then far apart. That's what's happening to air molecules when I shout and sound goes through air to your ear, like forgetting about the computers and everything. That, in that case of air, in the case of sound going through air, there the oscillation is parallel to the propagation. So that's not transverse anymore. We call that longitudinal or compression, because that's what's really happening is you're sending a little pressure pocket, like close together, far apart, close together, far apart. So you're sending little pressure pockets. So in the case of sound, just as like a sidebar, but just so you know, so we're not lying to you, all of the math, everything that we're saying about waves and all of the graphs all totally apply to sound waves. All the graphs, the cosines and all that. It's just that what's on the y-axis of the graphs isn't anymore really y position in space. It really stands for now like pressure, like measured in newtons per square meter or whatever. So it's all the same relationships. It's just that the dependent variable is slightly different. It's pressure, not height. Just so you know. So when you're picturing sound waves, you picture a compression wave going like this, but you could still draw the same graphs and all that. Okay, that's number one. Just to know, sound is a compression wave and the medium is air. Once we say the medium is air, and we say it's air molecules at like standard temperature and pressure, we can immediately say, oh, that all air molecules vibrate or oscillate. Like all air molecules are like little masses on springs. They all have like an effect, a little K and a little M based on their temperature and pressure. So all air molecules will have a specific omega. They'll all vibrate at a certain rate. Therefore, we can say, if you're talking about shouting, if you're talking about my tongue vibrating air molecules that then shake other molecules, that shake other molecules, that shake and go all the way to your ear through the air at standard temperature and pressure, we can then say, oh, the speed, this is the last thing I'm gonna, we could say like the speed of sound, like the speed of sound relative to air, we know is approximately 340 meters per second. And that means that, and like we can rely on that as a constant number because of all the logic I've already been saying. And what it means is that is how fast sound travels relative to air. Like if the air is then doing something, like if it's a windy day or you're rushing through the air or past the air, then you would observe a different number. But relative to the air, sound always travels at that speed. Okay, that's number one. I'm almost at the chat thing and I'm almost at some math thing. And I do see we have 13 minutes. But then the next thing I have to say about sound waves. So I'm just like being specific now, since sound is such a relatable version of a wave that we're going to spend, that let me also then say the frequency of a sound wave, as it says here in Brown, gets interpreted by the human brain as pitch or note, like highness or lowness, right? But or like what some of you might call tone, but that's actually kind of a specifically sort of a different thing. But like basically note is frequency. Not basically, like exactly, like literally, like and again, I know everybody knows music to different levels, but a lot of you play instruments, some of you don't, some of you have played instruments, some of you sing, right? But you all listen to music, like we all, right? And you know when a song is wrong. I mean, if you go to karaoke, like, you're even if some of you have perfect pitch, I'm sure. I don't have the time to find out right now, but like some of you may think that you don't know anything about pitch. You might think you don't know anything about notes or like what the notes are called on a piano keyboard or whatever. But if someone played your favorite song or tried to do it karaoke and they messed it up, you'd know it, right? Like, the difference between a wrong note and a right note at a certain level, even if you don't know what their names are. So I'm talking about that. I'm talking about notes, high and low, and I'm saying like literally, and some of you know this, if a piano is properly tuned, if it's not broken, if it's properly tuned, and you go over and you press middle C on a piano, and someone with a good sense of pitch goes, oh, yep, that's right. That's a middle C right there. What they're really saying is, oh, the air vibrated at 256 cycles per second. Like that's literally what a middle C is. It's 256 hertz. And a middle A, for also example, but more important in the history of Western music, middle A is I wrote 400. I'm sorry. I did not mean to write that. I mean to write, I'm surprised no one, 440, technically 440.1, whatever. A middle A on a piano, to tune a piano properly, is to make sure that the A in the middle of the keyboard is literally creating a situation that is vibrating ultimately our ear at 440 cycles per second. And someone with perfect pitch knows when it's off. I'm not saying they're doing math. Someone with perfect pitch, when they go, ooh, that A is a little sharp, like it's a little high. I'm not saying they're doing math, but if they go, ooh, that's wrong, that's a little bit sharp, what they are saying is, ooh, that vibrated a little bit too many times. I may not do math, but my body knows that those vibrations were too high. It's supposed to be 440. And then if you have a digital tuner or whatever, like you can like verify these things. And by the way, similarly, like if you know anything about, if you go an octave up on a piano from the middle A, and you hit the next A that is also an A but is higher, what is that? That's 880. It's a multiple of 440. I mean, this could be it is a whole class unto itself. It could be a whole course, right? Like all of music fits into math this way. My point for the moment, it's not vague, it's very precise. But my point for the moment, with 10 minutes left, and I want to get to the chat question, but my point for the moment is what we register sound frequencies, cycles, like hertz, our brain registers as notes. The higher the frequency, the higher the note. That's the first thing you have to know. The amplitude of the wave squared is what ultimately gets registered as volume. I'm saying that off in the margin here on the side. I'm saying it so I'm being factual and to give you perspective. Our focus for the Doppler effect, however far we do or do not get today. And of course, by the way, again, remember, even if I don't finish today, like the homework is due next Monday, so don't, I'll at least get to the chat question. When we start doing the math with these what we're concerned in the Doppler effect is that what we're really saying, the Doppler effect, what we're really saying, okay, here almost comes the chat question. What we're really saying in the Doppler effect is, okay, so back up for a second. Let's say, we're not talking about sound or anything, we're just saying, I'm at Coney Island. And I'm at on the beach, and there's an ocean, so there's waves coming in. Let's say I'm standing there and I observe, oh, 3 waves are coming in every second or every minute, whatever. Like, oh, and I'm counting, and they're pretty steady, let's say. 3 waves every second. Well, doesn't it make sense that if I start running toward the water, I'm going to hit the waves more, I'm going to encounter the waves more frequently than if I just stand there, right? And that's true. Then that's not a trick, and that's not an illusion. It's straightforward. If the waves are going 3 cycles per second, 3 crests per second, relative to the thing that made them, whether it's a storm or a boat or whatever, or someone's like tapping on the water and sending ripples out, if someone's standing in the water somehow making ripples come out 3 every second, I'll receive 3 every second as long as I'm standing also still relative to the water. But if I start running into the water, of course, I'm going to be, as the wave is coming in, I'm running in to meet it. So I'm going to encounter the waves more often. And similarly, if I run away, I'm going to encounter them less often, right? So if I have motion relative to the medium, I am not going to agree. I'm going to get a different frequency measurement from that which was producing the waves. I'm saying now sound works just like that. If you bang on a horn of a car and you send out the note A, middle A on it, like if the note from the horn is an A, that means you're sending out a sound that's going out, that's vibrating air molecules at 440 times per second. Again, that's not, by the way, that's literally true. That's not a random example. But so if you send out an A, then from your measurement, if you have a digital tuner or something, you'll clock that the sound is vibrating the air at 440 cycles per second, and you'll hear middle A, like eh. But if someone's running towards you while that happens, or you're running toward them, or the car is driving toward them, they're literally encountering those sound crests more frequently. So they will, if they're coming toward the car, or the car is coming toward them, they will receive a higher frequency than that which was sent. And that means they'll literally receive a higher note than that which was sent. If you drive a little bit fast, they'll get an A sharp instead of an A, if you know what I mean. And if you drive very fast, maybe they're going to get a B instead of an A. I don't mean they're great. I mean the note, right? So if I don't even do any math today, first of all, this is what I'm saying. What the Doppler effect is the idea that either the source or the receiver has motion relative to the medium for the sound for the wave. So therefore, the source and the receiver don't agree on the frequency. And if we're have different measurements for the frequency. And if we're talking about sound, that means they're going to experience different notes. So in New York City, if a motorcycle comes towards you and then passes you and goes away, everybody thinks it has something to do with where the motorcycle is. It has nothing to do with where the motorcycle is. And a lot of people think that the Doppler effect has something to do with how loud. It has nothing to do with loudness. The point of the thing of the Doppler effect is that when the motorcycle is coming to you, what you hear is a higher note than what the motorcycle hears. And you wouldn't even notice that. You wouldn't care at all. You wouldn't know because you're not the motorcycle. You're just you. So the motorcycle's hearing like, eh, and you're hearing, eh, and you wouldn't care, except that then the motorcycle passes you. So now the motorcycle's going away from you. So now you hear something lower than what the motorcycle hears. And again, you're never comparing yourself to the motorcycle, but you now hear something lower than what you did a moment ago, right? So the sound you hear when a motorcycle passes you, and I'm not talking about volume. and I'm saying, assuming that the motorcycle just maintains a constant speed the whole time, then first the motorcycle is constantly coming toward, then the motorcycle is constantly going away. So you hear like that, right? Like it's like its own little mini siren, even if it isn't a siren. That's the Doppler effect. Now, since we have four, I hope that makes some sense. We haven't done the math yet. We have to do the math. Next period, we'll do the math. But here, the thing to end on with 4 minutes is a question in the chat. That's a very important question. The question in the chat is, so when they experience different frequencies because they are in different reference frames, which is what I'm saying. And by the way, the they here is source and receiver. Like, so I'm going to when the source and the receiver experience, which by the way, I'm going to say measure two different frequencies because they are in two different reference frames, meaning that they're both going at two different speeds relative to the medium for the wave. Then the question in the chat, the very good question in the chat says, which is the one, like, what is it, the source or the receiver that is actually experiencing the correct frequency or pitch? I'm going to say that again. The question in the chat is, which is the one, the source or the receiver, that's experiencing or measuring the correct pitch? The reason I'm so pleased that someone would ask that with 3 minutes left, or that I would deal with it with 3 minutes left, is it's a super legitimate question. It's like the heart of the whole issue. But here's the thing. The answer is neither both. Both neither. Beither. Noth. Like, and I don't mean that to mock the question at all. Again, I'm like dead serious that it is exactly the right question. But this is the depth of relativity. That is literally like they're both correct. They're both like so correct. Okay, in fact, let me just be concrete for a second. Like literally, if a motorcycle were coming toward you and they had a tape recorder on the motorcycle and you have a tape recorder. In fact, we used to do this years and years ago where I taught, like not in New York City. We used to do this if you each had tape recorders and you turn, or whatever, iPhones, and you turn them on. Well, that shows you how many years ago we used to do it, whatever. And you both turn them on while the motorcycle, and so the motorcycle going, while it drives to like a person standing on the sidewalk. Like not only if you put, wait, well, that's what I'm explaining right now. Wait, oh, so someone just, can I explain why it's neither or both? And I can also hang out after class, absolutely. But I'm explaining right now. Well, first of all, I'm saying the demonstration is you could both record, and both recordings, if you then put the tape recorders or the iPhones next to each other when you were done, they'd be two different sounds because they're both real. They're both real. And the real reason they're both equally correct, neither one is any more correct than the other, is they're each a measurement being made in a different frame of reference. And the whole thing of Galileo that is very hard to absorb. It is hard to absorb, but it's really the essence of physics, is that all unaccelerated frames of reference are equally legitimate because the laws of physics are the same in all unaccelerated frames of reference. In other words, and I'm not mocking the question, it's a super important question, but the question is equivalent to asking which is more true, that the Earth goes past the sun at 65,000 miles an hour, or the sun goes past the Earth at 65 miles, or which is more true, the Earth goes past the sun at 65,000 miles an hour, or the Earth is still relative to itself. They're both equally true. Like, or which is more, and I'm not mocking it. It's very hard. At some point, all of us, this is where Einstein comes in and everything. At some point, all of us have difficulty getting our mind around this, but there is no center to velocity. It's why Galileo was put under house arrest for the rest of his life. Like, as opposed to being burned to the stake because he made it. Like, it's a very hard idea to accept that there's no center, but it is the physics idea that I could say I'm taller than you, or I could say you're shorter than me, and they're both equally true. Sorry. Yeah. Oh, it does make sense. Oh, good. I'm very glad. Okay, now look, I'm glad at least the person that asked this seems to be okay with my answer. But look, to all of you, and I'll continue this next time. I am yelling because I'm so excited because it's like the essential question of physics. It's literally why, I mean, I'm not exaggerating. It's why Galileo is Galileo, and like why he had to like fight the whole world on this, because it's a super hard idea for everybody. Okay, no, for everybody, and we'll get back to this. Maybe we'll pick right up on this after you like turned in your exams Wednesday. Maybe we'll have like a slightly more informal conversation about it, but then we'll do the math. And it's like my background research. I'm telling you, for everybody, including Einstein, there's a point at which if the example gets tricky enough, for all of us, we're like, wait, really? Wait, really? But that is what we are saying. So there's nothing more worthy of talking about in physics. So don't pretend. I'm not trying to pretend it's easy. But I am saying the idea is that velocity is a comparison between two objects. It's not an absolute property of either one. So nothing has an absolute 0 velocity, nothing has an absolute 3 velocity, and therefore nothing is an absolute A or an absolute C. It's an absolute A note in this perspective, and it's a C note in that perspective. And as long as the perspectives are constant, they're both equally legitimate. This is what makes physics hard. It's what makes it interesting too, but it's not the math. This is what separates physics from just raw math, that idea. So it's a great question. And if you still don't get what I'm saying, that's fine, but remind me on Wednesday. But anyway, good luck with the rest of your exams. And I'll hang out for a second if anybody wants to ask anything else, but have a great Queen's on time. Okay, have a great day. But I'm still, thank you. And I'll turn off the recording, but I'm still here. I'm just changing the view, but great question. Okay, great questions. Great. Hold on, I'm stopping the recording.